Hello, everyone. Can you hear me? Yeah, thanks. Yeah, it's been maybe 10 days after the last class because we had Chuseok holidays. I hope everyone had happy holidays. Okay, and then also as I announced, I posted the recorded video that I missed maybe as a Monday. So the posted video is for day 5 class. So actually at the day 5 class, we complete the chapter 1 of the textbook. So today we will cover the chapter 2 instruction of the computer systems. Okay. Also, as we complete the chapter 1, so I will post the first homework assignment for chapter 1. The homework questions will be very similar to the exercise question in the exercise questions in the textbook. So, and then please solve the homework questions by yourself because it's very important. Okay, so you need to solve the homework questions by yourself. Okay. So I believe so I believe so I believe the level of the exams will be very similar to the homework questions, the level of the difficulty level of the homework questions. So if you can solve the homework questions by yourself, I believe you can get a good scores in the exams. Okay. Okay. Any questions? Okay. So I will briefly review the day 5 class. So actually at the day 5 class, we covered the Moore's law. So actually the Moore's law is a very important law in the computer system industry or some semiconductor industry because the computer processor have read the semiconductor technology. Also, and then by the vice versa, it's also true. The semiconductor technology have read the advanced in the computer processors. Okay, and then actually the Moore's law is very important. Actually, it's not a theoretical law. It's some empirical law. So empirical law means that the law is established based on observations. Okay, so actually the Gordon Moore, he was a CEO at Intel, the very famous CPU company. So actually he observed the advanced in semiconductor technology, and then he made a law called the Moore's law, like the number of transistors will double every 2 years. So you need to focus on this double every 2 years and the number of transistors. So that means in the same CPU chip, the single CPU chip, the number of transistors will double. So that means that the number of transistors increases exponentially. So it's a very rapid advances. Okay. So why this is important? So usually as I mentioned, the advanced in the processor technology or some process performance is driven by the advanced in CMOS transistor technology. That means the semiconductor technology. So if we use better CMOS transistors, then we can make better processors, usually. So also we make a better architecture. but actually the common base of the performance improvement is read by advanced in semiconductor technology. Okay? Because if we use the small transistor, there are many benefits such as the dynamic power, also the speed of the transistor, that means the frequency. It is related to the frequency of the digital circuits. Also the power, we can reduce the dynamic power. Also we can reduce the supply voltage. But it's not easy recently. So many scientists or many engineers tell that the Moore's law is ending recently because it's not easy to make smaller transistor. So I believe everyone heard about the 5 nanometer technology or 7 nanometer technology by TSMC or Samsung, but we think that it will be very difficult to under this under 3 nanometer or 2 nanometer technology. So we are facing some limitation of some CMOS transistor manufacturing. Okay, so Moore's law is ending. So that means that the semiconductor industry or the processor industry will change in the near future. Okay, that's why the computer architecture or some computer system research is very critical for the advanced in some computer industry. Okay. Okay. So the textbook summarized the 8 great ideas in computer architecture. So actually, the computer architect, that means some engineers that study the computer architecture field. So computer architects focus on performance improvement based on these 8 great ideas, like so design for Moore's law, abstraction, and common case fast, parallelism, pipelining. So we will learn about the pipelining in chapter 4. Also the parallelism in chapter 5. No, chapter 6. And then also hierarchy of memories. So we will learn about the memory hierarchy, okay, in chapter 5. So these are very important ideas in computer architecture field. So the last idea, the dependability, is related to the reliability. Okay, so reliability means that the computer processor need to make the correct answers. Always need to make correct answers. Okay, that means the reliability. So you may think, oh, there must be, but so it's a machine. So also the computer system is a machine. So if we use our computer systems very long time, then the semiconductor, that means the computer chip, also wear out. That means it's a wear out means that it's a 낡아진다. Okay, so sometimes the computer may generate the incorrect answers. So it's related to the reliability. Okay, but in this course we will focus on the this pipelining, hierarchy, also abstraction, maybe. And then also you need to focus on this common case fast. It's very important. Okay. Okay, we complete chapter 1. Okay. So for this, in the today's class, we will learn about the instruction set architecture. So actually, in the previous class, I briefly explained about the instructions of a computer system. So instruction is just an instruction. So if you think about the calculator, it's a calculator. So how can we use the calculator? We just give the operands. Operand means the numbers to be calculated, and then we push some operators. So it is related to the instruction actually, operator, such as the plus, minus, multiply, and division. So these are the operator. So when we use a calculator, we give operands. So that is those are numbers to be calculated, and then we give operators. It's arithmetic operators. So it's actually instructions, because we give what should be calculated to calculator. Okay, we give what should be calculated or computed to calculator. So what to calculate is actually that means instruction. So computer, this is a processor. Processor also receives instructions. What are instructions? What are instructions? So actually, we write a program with high-level languages, high-level programming languages like C. So like main function, and my writing is not good. Print hello. Like this. So this is an example of a high-level language program. And so this high-level language program is translated into group of instructions which can be understood by computer hardware. So I mentioned instructions which can be understood by computer hardware. So these are instructions. Okay, so instructions. So by compiler, these high-level language programs are compiled into a group of instructions, and then these instructions are given to the processor. So if processor receives instructions, processor generate result. So I mentioned that the generated result are change of states. That means data in register file or main memory. So we will learn about the register file or main memory in this chapter. So actually data is a state, and then if the instructions are executed by computer processor, these data will be changed. That means the change of states. Okay, so that means actually, in other words, the data is given with sorry, my writing is not good. Data is plus some operator are given to processor, and results are generated. Okay, the answer. So that means it's also data, but it's a computed data. Okay, so it's this figure shows how computer processor work. So data plus operators is the instructions, and then instructions are given and results are generated. That's it. It's just very simple. So in chapter 2, we will learn how the instructions are created or instructions are made for computer processors. Okay, So that's instruction set architecture. So actually in the previous class, so it's also the review of the previous class. So instruction set architecture, which is called the ISA. It's actually the set of instructions. So it's a set of instructions, and then it also defines some other parts like the number of registers or the width of the memory address. So size of the memory space is also defined in instruction set architecture. Also, in the previous class, I mentioned that the instruction set architecture is the interface between software and hardware. So that's interface. So how can we define an interface? So there are two different words. So if something connects to these two different worlds, then this is called the interface. So in order to make some proper interface between different two worlds, we need to define some protocols. So protocol is something like promises or law. So these protocols are actually instruction set architecture between software and hardware. So that means the software write the code or program based on the instruction set architecture of a processor. Then instructions are generated using a compiler. Okay. Then the hardware received these instructions. Then hardware need to generate the proper answers or proper result based on the instruction set architecture. So if the hardware generate the incorrect answers or incorrect result, then the software will work incorrectly. So even though we write the correct code or correct application, if the hardware does not work defined by instruction set architecture, then our software will generate incorrect result. Okay, so that's why the ISA is called the interface between software and hardware, or the protocol or promises between software and hardware. Okay, so and then in this course we will learn about RISC-V. So this is the RISC type ISA. So if you're interested in this type of ISA, then you can see these slides, or you can watch YouTube video here. Okay, and then I also briefly explain about the RISC-V ISA. So what are most popular ISAs in the world? So x86 and ARM. So I will frequently mention two popular ISAs in this course, the x86 or ARM. So x86 ISAs is widely used for desktop or laptop or server computers. So, and then x86 CPUs are manufactured by Intel and AMD, the two major CPU companies. And then how about ARM? ARM is widely used for smartphones or some mobile devices like smartwatches, smart speakers. Also, the ARM processors are widely used for embedded systems like smart televisions, washing machine, smart washing machine, smart air conditioner. Like, so that's electric devices actually. So we prefer smart devices, and these smart devices also embed ARM processors. Okay, so ARM processors are widely used for mobile devices like smartphones, and then ARM processors are manufactured by Qualcomm, Samsung, so two major companies. Also NVIDIA. NVIDIA also makes some ARM processors. Okay, so these are two popular ISAs. Okay, so what we learn about the RISC-V. It's not popular now. It's not popular currently, but it's an open source ISA, open source instruction set architecture. What does that mean? So actually the x86 and ARM ISAs are commodity ISA. It's not free. So if we use these x86 or ARM ISA, then we need to pay royalty to Intel or ARM companies. Okay, it's not free. But RISC-V ISA was developed by university like UC Berkeley. So and then this RISC-V ISA is designed for research or education or some also for commercial processors. Okay, so many industry companies such as NVIDIA, or Western Digital, Samsung, some very popular companies are very interested in using this RISC-V ISA because it's free. So if these companies make some processors using ARM ISA, then they need to pay royalty to ARM company. So, but if they use the RISC-V, it's free. So x86 is also the one of the popular ISAs. So CISC type ISA. So CISC means complex instruction set computers. So as you can see, it starts with complex. So it represents, so this ISA is complex. It's not easy to understand. So that means the structure of the ISA is not simple. Okay, that means complex. So and then it's not free, and then there are 1,300 instructions, over 1,000 instructions. Oh, so many instructions. And then how about the instruction length? That means the size of one instruction. Okay, it's the instruction length varies from 1 to 15 bytes. So some instructions have 8 byte, 1 byte length. That means the 8 bit. Okay, so and then some instructions have 15 byte. Okay, this is very long instructions. So it's complex, it's not free, so it's not easy to learn this x86 ISA. And then ARM ISA. ARM is the simpler because ARM ISA is a kind of RISC type ISA. RISC. That means the reduced instruction set computers. Okay, so reduced. So compared to the complex, this RISC ISA starts with reduced. So that means it's the simpler type ISA, instruction set architecture. But ARM ISA is not free either. It's not free. And then number of instruction, so about 400. So it's smaller. The number of ISA of the ARM ISA is smaller than x86, but it's still many. There are many instructions. Okay, but RISC-V ISA was developed recently, and then so RISC-V has a simpler structure, also small number of instructions. Okay? So these are the features of RISC-V ISA: simple, clean, and then modular ISA. But then what does clean mean? Simple. It's a simple, a smaller set of instructions. And what does clean mean? Then x86 is a dirty. Because as you can see, this commercial ISAs has many instructions, support many instructions. Why? Because these commercial ISAs has long histories. So many instructions are added year by year. So if new instructions are required, then these new instructions are included in the existing instructions. So that's why. So there are so many instructions in x86 or ARM because the history is long. But the RISC-V it was developed recently. So RISC-V maintains the clean state because the history is short. Okay, clean and then modular. Okay, so the modular means that the RISC-V ISA has some different extensions. Okay, let's start from the base ISA. So base ISA is the integer ISA. Integer. What is the opposite of the integer? Floating point. So integer means 정수 in Korean. Floating point means 소수 in Korean. Okay. So the base ISA of the RISC-V is the integer ISA. So that means that these instructions of integer ISA just support the integer operations. But you may think, how can we use the floating point numbers? So we frequently use the floating point numbers also, like float a, the a equal 0.0001. So we frequently use the floating point numbers. So if a processor just support the integer type ISA, then these floating point computations are converted into the integer type computations. Okay, so for example, the floating point type additions are converted into the integer type additions that have many lines. Okay, but the baseline ISA is the integer type ISA because it will be very simple. And then with the integer type ISA, then we can learn the very simple architecture of computer processor. So the baseline ISA of the RISC-V is the IV32I, IV64I, IV128I. I means the integer. And then what does this number mean? This number represents the width of register file. So we will learn about the register file today. Maybe today or next class. So actually, this number represents the bit width of basic operand. So that means that if the IV32I just handles the 32-bit width operands, like the numbers have 32-bit width. Okay. And then in this course, we will learn about the 64I. Okay. And then 32E is the 16 register subset. Actually, the RISC-V has total 32 general purpose registers, but 32E is just has 16 registers. And then this baseline ISR has only about 50 instructions. So compared to the 1300 or 400, it's just 50 instructions. It's simple, okay? And then there are many extensions on RISC-V ISR. So M means the multiply, A means atomic, so F means the floating point, single precision floating point, D is a double precision floating point, and then G means the general purpose ISR. So that includes the IMAFD, okay? And then this slide just compares the ARM ISR and RISC-V ISR, okay? So to summarize, this slide shows that RISC-V is simple, okay? The total number of instructions is about it's less than 200 compared to ARM V8. And then this slide shows the baseline RISC-V ISR. So also I will also post this reference card on Piazza after this class. So also you can find the green card of the RISC-V reference card in the first page of the textbook. So this reference card shows the category of the instructions and then name of instruction and format, and then how the instructions are represented for assembly. Okay, so for example, this is the add instruction. So just add instruction. It has the R format. So we will learn about also R format in this chapter. So then, and then if we represent the add instruction like this. Add. So this is the name of instruction. RD, RS1, RS2. So this is the R format instruction. So in the R format instruction, so R format has the three operands. So one destination and then two sources. So these are two sources, and then this is the destination. The meaning of this instruction is the RD equal RS1 plus RS2. Okay. So if you see this RISC-V reference card, you can find many different instructions, but the number of instructions is smaller compared to other ISAs. So you can find the format and how we represent the instructions for assembly. Okay. 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 Let's learn about the arithmetic operations. So what are arithmetic operations? Arithmetic. In Korean, arithmetic means the 연산. So arithmetic means simply the operations such as plus, minus, multiply, to add, subtract, multiply, and divide. Okay, so these operations are called the arithmetic operations. So it's very simple, and then I believe you can understand well these arithmetic operations because we frequently use calculators. And then, as I already mentioned, if we use the calculator, we give operands and operators. So operators means the plus, add, subtract, multiply, and divide. And operands means the numbers. So 1 plus 2 equals 3. So these are operands and plus means the operator. Okay. Okay. And then these operations can be also represented with the instructions. Okay. So for example, the RISC-V has add instruction, like, and then as I also explained, the add instruction has 3 operands, like RD, RS1, RS2. Okay, and then this instruction, this is instruction. This instruction means RD equal RS1 plus RS2. Okay, and so these are operands. And then add means define the operator of instruction. And then how about other instructions such as sub instruction? Sub means the subtract. Okay, so subtract instruction has also the same format, like sub RD, RS1, RS2. Then I believe you can write the meaning of this code, like RD equal, there are 2 sources, but this is the first source, so RS1, this is the subtract RS1 minus RS2. So these are arithmetic operations of RISC-V ISA. So, and then these formats are called the R format. As you can see, this is the R format. So you can find other type of instructions here, exclusive or and. But you can find, oh, these instructions have the same format. So what does that mean? Actually, the kinds of instructions are different, but these instructions have the same format. So actually, only this part is different. Operand's part has the same format. So that means with this type of instruction, we can just change these operators. Okay, so for example, if we use the exclusive or RD, RS1, RS2, oh, this is the R format. So you can imagine that, oh, this is RD source, RS1, oh, it's exclusive OR. So if you took the digital logic design, then I believe you know what exclusive OR means, okay? RS2. Well, we don't know about the exclusive OR, but this exclusive operator is exclusive OR. So these arithmetic, actually this exclusive OR is not part of arithmetic operations, but these operations have the same format. So we can learn about the design principle. So design, it's not philosophy, it's a principle, just the principle. So what is the design principle? Simplicity favors regularity. So why regularity is important? So if different instructions have the same format or same regular formats, then we can make this structure of instructions simpler. So for simpler architecture or simpler structure, we need high regularity. Okay. And then why simple is better? Because if a structure is simpler, then we can make simpler hardware. That means the cost of hardware can be reduced. So I said cost is also important in engineering. So if we make the simpler hardware, then we can also reduce the hardware cost of processor. Okay. Okay. Let's see the example of this arithmetic instructions. So this is the C code, like f equal g plus h minus I plus j. It's very simple. So if this code is compiled into the RISC-V assembly code, how can we generate the assembly code? But it's very simple, okay? We can first perform this addition for g plus g and h, and then we can generate some temporal variable like t0. So the first instruction is add t0 gh. So it means the t0 equal g plus h, and also we can generate the result of I plus j for temporal variable t1. So the second instruction is the t1 equal I plus j. So here, so, and then we can perform the subtract instruction for t0 and t1. And it's very simple. Okay, so this is the one-line code of the C code, but this one line is translating the 3 arithmetic instructions of RISC-V ISA. Okay, so this example shows how the high-level language program is translated into the assembly code. Okay. Okay. Then before going operands of the computer hardware, we will take the pop quiz. So this pop quiz is the very simple quiz, and then so if you see the so if you visit the Blackboard, then you can find the pop quiz tab. Okay, and then you can submit your answers to this pop quiz link, and then the deadline of this pop quiz is today night. It's end of the day, end of today. It's about 11:59 p.m. So actually, I will use this pop quiz for attendance check. Okay, just the attendance check. So you can submit the simple answers through the Blackboard before 11:59 p.m. today. Okay, there are. So I will show this pop quiz questions through the Zoom, or also this will be also recorded, and then the YouTube video also will include these problems. Okay, so just see these problems, and then write down the answers, and then submit your answers through the Blackboard. And then I will give 3 minutes to write the answers. It's very simple questions about the chapter 1. Yeah. Yes. 토탈 3문제입니다. So there are total 3 questions. Okay. 그 블랙보드에 제출을 해야 되고요. 그 오늘 밤까지, 그러니까 엔드 오브 투데이니까는 오늘 11시 59분까지 제출하면 됩니다. Okay, I think it's enough. So actually we will have we will take a pop quiz randomly, so randomly in the middle of the class. So it's just to check the attendance of the students. Okay, so it's actually the points assigned to the pop quiz is not large. Okay, so please focus on focus on the class. Okay, every class. Okay. Okay. Oh, let's go into the next topic of the today's class. So it is the next topic of the today's class is about the operands of the computer hardware. So as I already mentioned, what is the operands? 1 plus 2 equal 3. So this is the arithmetic operation. So in this arithmetic operation, these numbers used for calculation are operands. Okay, so operands are actually, in other words, it's the data used for computation. Okay, so these operands, okay, then how computer hardware or computer processor use operands? How? So in this example, so this is an example of the RISC-V instruction. So as you can see, this instruction requires 3 operands. That means the 3 data. And then we already defined the meaning of this instruction, like RS1, RS2, or RS plus RD. And then what does RS mean? What does RS2 mean? What does RD mean? So we will learn about what RS1, RS2, RD are. Okay. So actually, when we write the instruction like RD, RS1, RS2, so these are operands, and then that means the data. Then this data comes from register file. What does that mean? So if you write a C program, then how can we write a program? Like B equal A equal 1, we write like A equal 1, B equal 2, and then C equal A plus B. So I missed the semicolons. So what does that mean? That means we store 1, 2 variable A, right? And then we store 2 variable B. Then that means this is the memory, so memory space. In the memory space, a certain memory space is assigned to variable A, is a memory space. And this memory space, we store number 1, right? And then in the B, we store number 2. Then what is the C? Oh, C has also its own memory space. And then store, first we calculate A plus B, and then store each result to C, right? Then it's 3 is stored to the C. So in the real program, in the high-level program, we define the variables, and then that means that these spaces for variables are assigned to some memory space, and then we store certain numbers to these memory spaces, and then we read the data from these memory spaces, and then calculate something. Okay, that's how programs work. It's same to instructions. So I mentioned that the data is stored in the register file. So here you can find the register file. So register file means it's small memory space inside of processor. Okay. So in this slide, you can find the arithmetic instructions use register operands. So that means that add RD, R1 or RS1, RS2, oops. So like C equal A plus B, this add instruction read data from RS1. So I said that this is the register operand. So that means that the numbers are stored in this register RS1. So that means there is a memory space called RS1. So actually, it's a RS1 called RS1, and then a number data is stored in this memory space. RS2 is the same. There are memory space called the RS2, and then another number is stored in this memory space. And what does add this RD, add RD, RS1, RS2 mean? So this instruction performs the read numbers from RS1 and then read number from RS2 and then performs add operation like RS1 plus RS2 and then store the result to the another memory space called RD. Okay, and then these memory spaces are called the registers. And then the set of registers is called register file. So these are small memory space inside of a processor. The RISC-V has 32. No, that means there are 32 registers. So there are 32 memory spaces. And then 64-bit means the width of the register. So that means the width of the register is 64-bit. So computer just handles the binary number, right? So bit means the number of bits in this binary number, right? So that means the 64-bit means that the numbers can be represented using 64 bits binary number. So RISC-V processor has total 32 registers, and then the width of a register is 64-bit. Okay, because so in this course we will learn about the 64-bit processor. That means that the width of the list of a register is 64-bit. So this actually we will learn about the R364I in this course. So I mentioned that this number represents the width of basic operands. Okay, so in this textbook we will learn about the 64-bit instruction set. So that means that the width of a single register is a 64-bit. So that means we will learn about the RV64I. Okay, and then there are 32 registers. So actually the RISC-V processor has 32 is called the general purpose. General purpose registers. So actually in the digital system design, its temporary memory space is called the register. Okay, that is also, so register means the temporary memory space, but the register is very fast, and then registers can be directly accessed by processor because the registers are located inside of a processor. It's very fast, but it's very small compared to the main memory. So think about the main memory. So what is the size of the main memory of your smartphone? So recently we have about the 4 gigabyte, even the 6 gigabyte or 8 gigabyte. Okay, so gigabyte, so it's actually very large compared to the 32 multiplied by 64-bit, because 64-bit is the 8-byte, and then there are 32 registers. What is the size of this register file? So 32 multiplied by 8 will be 156 byte. just 256 byte, right? Just 256 byte. It's about the 1/4 kilobyte. Okay, but main memory size is gigabyte. It's very large. So why do we require this small memory space inside of a processor? Because it's small, so it's fast. Smaller is faster. It's another design principle. So that means the number data is temporarily stored in this register file. It's a small memory space. So, and then if the data is stored in this register file, these data can be directly accessed by computer processor, and then the calculation is performed. Okay. So smaller is fast. That's why we use the registers. Okay. So I already explained about the definition of the register. So, and then, but I copied the definition of the register here so I copied the definition from the Wikipedia. So please read this definition, okay? Again, this slide shows the structure of a register file inside of RISC-V processor. So as I mentioned, there are 32 registers from X0 to X31. And then the width of the register can be 32 to 64, 128. So if we use the 32 width, then that means the IV32I. If we use the 64 width, then that means the IV64I is the IV128I. So, okay. And then, but this X0 is the special register. So that means X0 always gives zeros. Because this is the special register. So the value of the X0 is always 0. What does that mean? So even though we store like add X0, X1, X2. So what does that mean? This means that this is the source register. This is the destination register, like RD, RS1, RS2. So that means this operation, this instruction, read data from X1 register, okay, and read data from X2 register here, and then perform plus, and then store the result to X0. Okay, so if we store the result to X3, then X3 can be updated by X1 plus X2. But I mentioned X0 is a special register. So even though this data is stored in the X0, the value of X0 is always 0. Okay. So it's a special register. But except that this X0, these 31 registers are general purpose registers. So that means if we update some value, if we store some data to these registers from X1 to X31, then the stored data is updated to these registers. Okay. And then another special register is the PC. PC means the program counter. And then I will explain about the PC later, because so now I believe if you first take this course, then I believe you are not familiar with the PC. It's a program counter. So just to remember that PC is the special register, okay, program counter. Then I will explain about the PC later, okay. So in the RISC-V processor, there are 32 general purpose registers, including X0 plus PC, it's a program counter, okay. But even though these, so X1 to X31 is the X1 to X31 registers are general purpose registers, we use a certain registers as for special purpose. Okay. So it is also defined in the instruction set architecture manual. So for example, but these are recommendations, okay? Actually recommendation. So this recommendation is required for making compilers, okay? So compiler translate our high-level language program to assembler program. And then compiler assign the destination of the instruction using this high-level language code, okay? And then compiler use a certain registers for some specific purpose. So for example, we can use the X1 for the return address. So but now I believe you are not familiar with these terminologies, but just to see it, just to read it. So X2 is a stack pointer, and then we can use the X5 to X7 and the X28 to X1, the temporary registers, frame pointer, some specific purpose. Okay. Okay. So this is an example we used in the previous slide. So in the previous example, we just used the variable name directly from this C code. But now we can use the register numbers. Okay, so let us assume that for variable f to z is stored in the register number x19 to x23. Then we can rewrite this RISC-V assembly code like this. So G is stored in the register x20, H is in the x21. Then this computation is translated in the add instruction, and then we just store the temporary data to register x5. Okay, and then this is the same, and then f is in the x19. So the final result f is stored in the x19 register. x5 minus x6 equal x19. So we can rewrite this previous assembly code like this, okay, using the registers. Okay, so I will stop here. Do you have any questions? So we learned about the operands of register operands of the RISC-V hardware, and then in the next class we will learn about the memory operation of a RISC-V processor. Okay. Do you have any questions? Okay. 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 Thank you for listening, and then see you in the next class. Thank you.